Assalamu alaikum student. Today the lab task is about the construction of a non-sinusoidal oscillators and to analyze their output waveform using the hardware and the software tool. The purpose of this lab is to familiarize you with the working of the non-sinusoidal wave oscillator circuit, that is the 555 timer and the Schmidt trigger oscillator. These two oscillators are used to produce the square wave, which is a non-sinusoidal waveform. As I described in the previous section, that the oscillator basically is a circuit that will produce the oscillation without any AC signal just by using the DC power supply. It is also used in many type of the electronic equipment, for example the clock circuits, radio and the computer circuit. And the oscillator circuits output depend purely on the type of the circuit that you are using. It can produce any kind of the output signal, sine waves, square waves and triangle waves. There are the main type of the oscillator circuit, that are the linear circuit or the non-linear circuit. The linear circuits, linear oscillators are the harmonic oscillators, and the non-linear are the relaxation oscillator. Harmonic oscillators are discussed in the previous lab experiment. Here we will discuss about the relaxation oscillators. Relaxation oscillators are basically the non-linear devices that produce a non-sinusoidal output waveform. It can be square or triangle waveform. In the relaxation oscillators, the circuit consists of a feedback loop containing a switching device such as the transistor and the comparator, or the op-amp, that repetitively change the capacitor or inductor through a resistive nectar until it reaches to its maximum value to produce the oscillation. The time period of the oscillation that it will produce will depend upon the type of the capacitors and the inductors and the resistive component that you are using in the circuit diagram. Because the active component, whether it is capacitor or the inductor that you are using in your circuit diagram, will abruptly charge or discharge to produce the oscillations. Relaxation oscillators are basically used to produce the low frequency signals, such as used in the blinking light, electronic beepers, inverter, switching power supply and the function generator. To produce the square wave type oscillation, we will use two oscillators here, that is the 555 timers and this Schmidt trigger oscillators. Okay, let's discuss about the 555 timer circuit. The 555 timer circuit is used to implement a variety of the different timing function. It usually come in the 8-pin configuration, as is shown in the figure 13.1. You can clearly see that it has 8 pins. The dot or the cut at the top of this pin represent a starting point, and from here it is we can mark pin 1, which is ground, 2 for the trigger, 3 for the output and 4 for the reset. The pin 5 is for voltage control, and it is used when you will have any spikes or noise in your output. Pin number 6 is for threshold, 7 is for discharge, and pin number 8 for is VCC supply. Here the pin number 1, 4, 5 and 8 are used to establish the operation of chip which is producing the square wave, in which the capacitor charge or discharge to produce the square wave, and the pin number 2 and 6 are for the input pin, and the pin number 3 and 7 are for the output operation. Here in the figure 13.2 are shown, which I was describing, that which pin is using for which purpose. You can see that the pin number 2 and 6 are combined. Here 2 and 6 are used for the input, and pin number 3 and 7 is used for the output, and rest of the pin is used for the operation of the operation of the oscillators. Here in this circuit diagram, the pin number 5s are not used, but here we will connect a capacitor to ground if it will produce any noise in the circuit. The output that it will produce will be a square wave of the frequency given by this using this formula. Since it is producing the square wave which has the two parts, that is on time and the off time, and the on time for this oscillator is given by the formulas shown in the paper sheet, and the off time formula is also shown in the paper sheet. In this way you can calculate the overall time period of this square wave. To analyze the 555 timer circuit diagram, I just calculated its frequency of the oscillation using this formula, which come out to be 48 kilohertz, and then I calculated the on time of this circuit, which is 13.8 microsecond. Then I calculated the off time, which is 6.9 microsecond. Then I calculated the total time period, which is 20.7 microsecond. By using this I also verified the frequency, which comes out to be 48.09 kilohertz. Then I just assembled the circuit on the hardware using the circuit diagram, and then verify its cutoff frequency, its frequency of oscillations, and the on and off time. To verify the operation of the 555 timer circuit, I just assembled the circuit on the breadboard. Here these two resistors are used to maintain the duty cycle of the 555 timer circuit, and the output wave that produce, and this capacitor is used to maintain the frequency of oscillation. For this purpose, I just assembled the circuit on the breadboard. You can see that I use the two capacitor here and the two resistor here. These two resistors are producing the values of the duty cycle, that the square wave is of the square wave, and this capacitor is producing the frequency of the oscillation, and this capacitor is used to smooth the output waveform. If I didn't connect this capacitor, then there will be ripple in the output waveform, that is a square wave. You can see that I didn't apply any AC input signal to this circuit, because it is an oscillator circuit which will automatically produce oscillation using the DC power supply. I just connected this circuit with the DC power supply, that is 10 volt, and the output is displayed on the oscilloscope. You can see that here the square wave is generated with a duty cycle of 67.4%, and this duty cycle is depend upon the two resistor RA and RB that I used in the circuit, and this frequency depend upon the capacitor that I produced, that I used in the circuit. If I disconnect this capacitor from this circuit, then you can see that there is ripples in the output waveform. If I again connect this capacitor to the circuit, then you can clearly see that the output waveform is more refined than the previous. So this capacitor is using to maintain the frequency of oscillation, and this capacitor is using to refine the output waveform, and these two capacitors are producing the duty cycle of the square wave. So if I want to change the duty cycle of the square wave that generated, then I have to change the two resistors values. These two resistors value define the on and off time of the square wave, which is the time period of the square wave. So if we change the values of this capacitor, as I am doing in this, you can see at the output that now the frequency of the oscillation is different as previously described. So by changing the values of the capacitor, there is no effect on the duty cycle, only the frequency of the oscillation of square wave is changing. Our second task is about the Schmidt trigger oscillators. It is basically a comparator circuit implemented by applying a positive feedback to a non-inverting input of a comparator or a differential amplifier. It is an active circuit which will convert the analog input signal to a digital output circuit. The circuit is named as a trigger because the output retained its value until the input changes sufficiently to trigger a change. You can see that here I am using a trigger circuit and the feedback resistors are used and just only capacitor are used. By using this DC power supply, which is the 5 volt, where it will trigger and amplifies the electronic noise that will produce when we'll switch on this DC power supply. Then this noise will continuously fed back until it produces the required frequency of oscillation. Which type of the oscillation it will produce depend upon which type of the RC I am using here. This is the formula which is used for the frequency of the oscillation. In the lab task, we will verify the different frequency of oscillation using the different value of the capacitor. By changing the value of capacitor, we will actually using the frequency of square wave, which is generate here at the output. And this Schmidt trigger oscillators are basically used in the signal conditioning to remove the noise from the signal used in the digital circuit, because it will trigger at any desired point. In the lab task, we will use the 3 different values of the capacitor to produce a different frequency of oscillation. First, we will use the 1 nanofarad capacitor, then 10 nanofarad capacitor, then 1 microfarad capacitor, just to show you the difference between the frequency of oscillations. This second lab task is about the Schmidt trigger oscillator. It is another type of the square wave oscillator. The circuit diagram is shown in the figure 13.3, and this frequency of oscillation is given by this formula. This is an oscillator circuit, so we don't need to apply any AC input signal. It would automatically produce the output of at the output, which will be a square wave, by using the DC supply, which is the plus 5 volt. To verify that this oscillator produced square waves or not, I just assembled this circuit on the breadboard. The circuit is same as I show you in the figure 13.3. Here one capacitor is used and one resistor is used. The capacitor is 1 nanofarad and the resistor is 1 kilo ohm. And I just connected it with only with the DC power supply. There is no AC input applied to this source. When I connect this circuit, and then I saw the output and the pin number 2, then there will be a square wave with the duty cycle of 25 and the frequency of 553 kilohertz. It is due to the DC power supply of 10 volt that applied to this circuit. It is due to the DC power supplies of plus 5 volt that is applied to this circuit. Now the frequency of oscillation depend upon this capacitors, and the duty cycle will depend upon this resistors. If I can show you how this capacitor change the frequency of the oscillation. I am changing the capacitor from 1 nanohertz to 10 nanohertz. You can see that when I change the capacitor from 1 nanohertz to 10 nanohertz, then the frequency of oscillation will change from 790.5 kilohertz, while the duty cycle will remain the same, because I did not change the resistor value. I just changed the capacitor of the circuit. If I further change the capacitor to 1 microfarad, then again the values of the frequency of oscillation will change. Now it is in hertz, and while the duty cycle will remain the same. So we can conclude that the frequency of oscillation depend upon the value of the capacitor that we use here, and the duty cycle will depend upon the resistor that we used here. And it will behave as a square wave oscillator because it is producing the square wave. It is due to the DC power supplies of plus 5 volt that is applied to this circuit. Now the frequency of oscillation depend upon this capacitors, and the duty cycle will depend upon this resistors. If I can show you how this capacitor change the frequency of the oscillation. I am changing the capacitor from 1 nanohertz to 10 nanohertz. you can see that when I change the capacitor from 1 nanohertz to 10 nanohertz, then the frequency of oscillation will change from 790.5 kilohertz, while the duty cycle will remain the same because I did not change the resistor value. I just changed the capacitor of the circuit. If I further change the capacitor to 1 microfarad, then again the values of the frequency of oscillation will change. Now it is in hertz, and while the duty cycle will remain the same. So we can conclude that the frequency of oscillation depend upon the value of the capacitor that we used here, and the duty cycle will depend upon the resistor that we used here. And it will behave as a square wave oscillator because it is producing the square wave.